Welcome to AICE Chemistry lecture series. Today we're going to discuss chemical formulas and chemical equations, which is part of section 3.6 in chapter 3. Now, this section should be mostly a review from a mixture of stuff that we learned in honors chemistry. Everything from nomenclature to chemical formulas and that type of topic. So a lot of this is going to go by very quickly and it's not in as much detail because you should remember from honors chemistry. If you would like more detail or you would like to really dive more into it, please check your honors chemistry notes. So we're going to start with ionic compounds, and we need to remember that ionic compounds are going to be made out of ions. So they're going to be a combination of some anion and some cation, some of them monatomic, some of them polyatomic. So the polyatomic ions we need to remember are going to be things that we need to memorize. Things like ammonium being NH4 plus, things like carbonate being CO3 2-, bicarbonate or hydrogen carbonate being HCO3, etc., etc. And these are here some examples up to, except for the last two lines, of some polyatomic ions. Now, a lot of elements will also have what we call monoatomic ions. Monatomic ions are just the element itself with either missing electrons making them a positively charged ion or a negative electron making a negatively charged ion. For the representative elements like group 1 and 2 and groups 13 through 17, we can actually tell what the charge of the ion will be based on the group number. So group 1 elements have a +1 charge, group 2 elements have a +2 charge. Most group 13 elements, if they have ions like aluminum and gallium, will have a +3 charge. And then group 16 elements will be -2, 17 elements will be -1. And also not shown here, group 15 elements will have a -3 charge. So I believe this is nitrogen. Oh, let me do that not in yellow. I believe this is nitrogen, this will be N3-, this will be phosphorus, which is P3-, so on and so forth. Now, important to note that the noble gases do not have any ions that they make, because remember, noble gases don't tend to react very much, and so they will not create ions. So the non-metals on the right side of the periodic table will create negative ions, again, and based on the group number, we can tell which charge. And then the left side of the periodic table, the metals will create positive ions. And if they're representative elements, we can tell by their group number. Now, the transition metals, on the other hand, like zinc and silver, might not have just a single ion. Or if they do have a single ion, like zinc and silver, their charges are not something we can just tell from the periodic table. A lot of the time we'll have to remember them. So for example, zinc having a 2+ charge, that's just simply something we need to remember. And that usually will be obvious from the context of the questions. Same thing with silver having a +1 charge or gold having a +1 charge. Because it's a transition metals, we just kind of need to remember from our past dealings in chemistry, or simply by just looking at the context of the question, what the charge of the ion is. Now, what do I mean by the context of the question? Well, a lot of the time we're going to be looking at these ions in the context of ionic compounds. And you have to remember that when ionic compounds come together, they're going to be put together in a ratio that cancels out the charge of the compound, meaning the compound will have a neutral charge. For example, if we were to make a compound out of, let's say, aluminum, which is a 3+ charge, and sulfur, which is or sulfide, shares equals an ion, which is a -2 charge, then in order for these to cancel out, we will need the positive charges and the negative charges to even out. Since as aluminum is a 3+ charge and sulfur is a -2 charge, then we will need 2 aluminum ions, which has a +6 charge overall, to pair up with 3 sulfide ions to make a compound. Why? Because overall this has a +6 charge, whereas this has a -6 charge when we add them together. The +6 and the -6 will cancel out and give us the compound Al2, because there are 2 aluminums, S3, a 2 to 3 ratio. Now, we can also do something called crossing to make this process a little easier. And we're going to try this with a polyatomic ion now. But we could grab something like, let's say, no, let's not do ammonium. Let's do magnesium, Mg2+. And if we pair it with something like phosphate down here, PO4 3-, instead of trying to figure this out logically by using ratios and by using kind of the lowest common denominator, what we can do is we can grab the 3 from the phosphate and put it in the bottom of the magnesium, grab the 2 from the magnesium, put it in the bottom of the phosphate, and we'll end up with the right formula, which is Mg3PO4 2. And remember to put the PO4, the polyatomic ion, in parentheses when we put a subscript on it. So this is the right formula for magnesium phosphate, with a combination of the magnesium ion and the phosphate ion. We have to be careful with crossing though, because sometimes the charges will need to be simplified. For example, if we were to combine, again, magnesium, but this time we combined it with something with a 2- charge, something like, let's say, carbonate, CO3 2-, then when we cross magnesium and carbonate, the 2 goes on the carbonate, the 2 goes on the magnesium. But we have to remember that ionic compounds have the lowest whole number ratio possible. So Mg2CO3 2 is not a possible ratio for magnesium and carbonate, because we need to simplify this ratio to a 1-to-1 ratio, meaning the actual formula would just be MgCO3. So always remember that ionic compounds are simplified to the lowest whole number ratio. And we should also be able to do this backwards. If I'm looking at magnesium carbonate, I should be able to follow this logic backwards to arrive at the ions that I used. This is going to be especially important because some elements, and we can see down here, some of the elements are going to have variable ions. And what does that mean? That means that some transition metals like iron don't have just one, but 2 different ions associated with them. This is true of monatomic ions, of certain transition elements, and pseudo-transition elements, things like lead and tin, which are not officially transition metals, but do have multiple ions. But it can also lead to things, or it can also be related to things like groups or families of polyatomic ions. For example, the sulfate ion, SO4 2-, has a bit of a family because we have 2 different ions that have a similar conformation. We have sulfate, which is SO4 2-, and sulfite, which is SO3 2-. Similarly, we have groups of larger ions like the chlorate family, where we have hypochlorite, which is SClO-, chlorite, which is ClO2-, chlorate, which is ClO3-, and perchlorate, which is ClO4-. So when we have this distinctions of transition metal ions with various oxidation numbers, and we'll look at why we call them oxidation numbers in a later chapter. We can just call them charges for now. But when we have transition metals with multiple oxidation numbers, or this family of ions, which are similar ions but with multiple different ratios between oxygen and another element, we have to be careful of how we look at compounds. So for example, if we had a compound like, let's say, FeSO3, in order to name this, we would need to know what ions these are. And we would need to be careful and be very think really carefully about which iron this is, whether it's iron 2+ or iron 3+. We can figure this out again by using logic and looking at the anion, because anions, even though there are families of anions, they are always going to be only one charge. For example, the SO3 ion, which is the sulfite ion, is SO3 2-. And that's never going to change. That's always going to be the charge of sulfite. So as long as you know that, you can use the logic to figure out the charge of the iron, because if iron here is a 1-to-1 ratio with the sulfite, if the sulfite is 2 minus, then the iron, to cancel it out, has to be 2 plus. Because again, the charge is the overall positive, plus 2 here, needs to match the overall negative, which is minus 2. On the other hand, if we have a different ion of iron, like iron 3 plus, we'll have Fe 2 SO3 3. Here I have 3 sulfide ions, all of which have a 2 minus charge. So again, using logic and looking at this logically, this overall has a minus 6 charge. Meaning these irons, and I have 2 of them, these 2 irons together have to cancel out this minus 6 charge, which will be plus 6. And so if this is plus 6 overall, and there are 2 irons, then each iron needs to be 3 plus. So this is the difference between iron 3 sulfite, which is the 3 plus ion, and iron 2 sulfite. And you need to be able to work backwards and forward from the ions to the formula and from the formula to the ions. This is not just true of iron. There are multiple different transition metals that will fall under this category. Things like copper has multiple ions, vanadium, chromium, and many more transition metals. Lead, tin, which are not transition metals but are kind of like a pseudo transition metal. Moving forward. So that's ionic compounds, and that's a bit of an overview from honors chemistry, really, of what transition metal and ions and then ionic compounds in general kind of fall under. Now let's look at covalent compounds. Now we're going to look at covalent compounds a lot more later in chapter 4, but let's talk briefly about what we learned in honors chemistry. Covalent compounds are often going to be formed out of non-metals. So the main culprits here are going to be hydrogen, carbon, nitrogen, oxygen, fluorine. But really any transition non-metal can form an ionic covalent compound. So if we look at the periodic table, we have obviously hydrogen, which is a non-metal, but then any of carbon, nitrogen, oxygen, fluorine would be a non-metal, phosphorus, sulfur, chlorine, selenium, bromine, and realistically speaking, anything that is on the right side of the metalloid ladder could form, actually not tellurium, iodine. So any of these could form transition covalent compounds, and even some metalloids like silicon, like boron, can form covalent compounds as well. So this is a very small pool of elements to pull from to make these covalent compounds, but there are so many combinations that we can have. We can even, in certain circumstances, bring in krypton and xenon, which are noble gases and shouldn't react, and make them, force them to react to form covalent compounds. That's something new you're going to see this year. You need to be okay with looking at things that seem strange, like krypton or xenon forming covalent compounds, but are going to start being more commonplace. Because again, chemistry is not just black and white. There are a lot of shades of gray, exceptions, and things we can force to happen in nature. So, now their chemical formulas are often going to be deduced based on the number of electrons that each element has. And this is very important. Elements in the same group have the same number of valence electrons. And because they have the same number of valence electrons, they can achieve a certain number of classic or typical bonds. For example, hydrogen, which has 1 valence electron, but hydrogen being special because it only needs to copy helium, so it needs 2 valence electrons to be stable. Because hydrogen has 1 valence electron, it can form 1 bond. Group 14 elements having 4 valence electrons need 4 more to reach an octet, so they can form 4 bonds in total. Group 15 elements which have 5 valence electrons will need 3 more in their pairing or in their forming covalent bonds to reach an octet, so they'll need 3 bonds in total. Oxygen and any group 16 element will need 2 bonds. Again, why? Because 6 plus 2 equals an octet. 5 plus 3 equals an octet. Because remember, every bond that forms brings in 1 valence electron to this element. 4 plus 4 is an octet, right? And then 1 plus 1 for hydrogen, because hydrogen only needs 2 valence electrons. It's an exception, not 1. And so group 17 elements, like fluorine, will only need 1 bond to form an octet, because when you form 1 bond, you bring in 1 electron. That gives you 8 valence electrons in total. So for example, if I had carbon and hydrogen bonding together, carbon will be in the middle, and because carbon can form 4 bonds, I will have 4 hydrogens. And that was why carbon makes CH4. On the other hand, if I have nitrogen and hydrogen, that will make ammonia, NH3. Why 3? Nitrogen naturally has 1, 2, 3, 4, 5 electrons. And so the ones at the top are already paired up, so they're going to be stable. They're going to want to stay paired up. And so these 3 which are not paired up, oops, so that was my nitrogen. These 3 which are not paired up are going to then be converted to bonds to pair up with those hydrogens. That's why nitrogen and any group 15 element, because they're all going to have 5 valence electrons, can only form 3 bonds. Now, this is a rule that we're actually going to break later on, and you can see here that it says on the PowerPoint that there are exceptions to these rules. We are going to look at the exceptions later on in Chapter 3 with things like expanded octets and beryllium and boron being special circumstances where they're electron deficient, but we're not going to worry about that till Chapter 4. What we want to worry about here is learning the typical number of bonds an element will have. So, and then learning that if they're in the same group, they're going to behave similarly. Because here I have how a group 14 element like carbon and a group 15 element like nitrogen behave differently. But what if I brought in another group 15 element? What if I was talking about the combination between phosphorus and hydrogen? Well, phosphorus is also in group 15. So because phosphorus is in group 15, like nitrogen, they're essentially replaceable in each other. So if nitrogen forms a 1-to-3 ratio with hydrogen, phosphorus is going to form a 1-to-3 ratio with hydrogen, because they're in the same group and they can form 3 bonds. So when I draw the phosphorus molecule, and again we'll do a lot more drawing of Lewis structures in Chapter 4, but when I draw the phosphorus Lewis structure, again it's going to look exactly like the nitrogen one, because they're in the same group and they form the same kind of bonds, and the same number of bonds, and the same conformation of bonds. So the idea here is to learn the classical or the normal number of bonds that a special group will form, because that's going to make it a lot easier in Chapter 4 to create these molecules. So let's move on. So this is a kind of question you might be asked in the AS exam. This is a paper 2 question, and it's not as direct, right? It's not straightforward as you would think or hope for this type of topic. It says here, a compound of fluorine and oxygen contains 3 atoms in each molecule. Predict its formula. So let's bring up a more workable version of this. So it says here that a compound of fluorine and oxygen. So let's make it purple. We're working here with fluorine and with oxygen. Fluorine is a group 17 element, whereas oxygen is a group 16 element. Now, if we again look at our PowerPoint real quick, we can see that group 17 elements make 1 bond, and group 16 elements make 2 bonds. So we can go back to our question. So we have a group 17 fluorine, group 16 oxygen. That means fluorine has 7 valence electrons because it's in group 17. Oxygen has 6 valence electrons because it's in group 16. And so we can tell just from this how many bonds they're supposed to make. Fluorine being in group 17 is supposed to make 1 bond, because that 1 bond will bring in 1 extra electron, giving it an octet or 8 valence electrons. Oxygen being in group 16 is going to make 2 bonds, because those 2 bonds will bring in 2 extra electrons, making 8 valence electrons in total. Now, you have to be careful with how you read this question, because this right here might confuse some folks, or some students. A compound of fluorine and oxygen contains 3 atoms, not 3 bonds. And what's that? You have to be very careful with the wording and what you're reading. It's 3 atoms in total, not 3 atoms of oxygen, not 3 atoms of fluorine, 3 atoms in total in each molecule. Which means that when we're looking at this, we're going to have 3 things bonded to each other. Well, that's where this comes into play. If we think of the ratios, we got 2 bonds for every oxygen, 1 bond for every fluorine, and we have 3 atoms in total. If we think of oxygen, because it can form more bonds being the central atom, and that's kind of what we have to do here, is think of that oxygen as our central atom. If we think of oxygen as our central atom because it can make 2 bonds, then if we form 1 bond to one fluorine, 1 bond to the other fluorine, then this oxygen is now happy, because remember, oxygen originally had 1, 2, 3, 4, 5, 6 valence electrons. And then we have fluorine with 1, 2, 3, 4, 5, 6, 7 valence electrons. If we picture we have 2 of those fluorines, then 1 bond can be created here, the other bond can be created here. That gives fluorine 2, 4, 6, 8 electrons. This fluorine 2, 4, 6, 8 electrons. And then oxygen 2, 4, 6, 8 electrons. So everyone's happy with this new conformation of fluorine and oxygen, meaning that this meets all of the requirements. There are 3 total atoms, like the question said. 1 fluorine here, 2 is the oxygen, and 3 is the second fluorine. 3 atoms in total. And the oxygen has 2 bonds, and the fluorines have 1 bond. Everything has an octet, so it's a very stable molecule. So what is the formula? Because you got to be very careful again. This is not the Lewis structure they're asking us for. They're asking us for the formula. Then the formula is going to be OF2. Or alternatively, you could say F2O. In this case, it doesn't really matter which one you use. But again, how do we figure this out? We figure this out based on what are the normal number of bonds that these elements make. And why do they make those bonds, that many bonds? Because of how many valence electrons they have. Remember, what guides this bonding in covalent bonding is the octet rule, which generally speaking means that everything wants the same electron configuration, or actually specifically speaking, it means that everything wants the same electron configuration as a noble gas. Now, normally that means 8 electrons, except for hydrogen, that means 2 electrons for hydrogen. Most things only 8 electrons, because most noble gases have 8, actually to say valence electrons. But for hydrogen, that's going to mean 2 valence electrons, or electrons in total, because hydrogen only has so many electrons. All right, and that's how we answer this question. And we can see this in the mark scheme. I'm going to go back here. If we look at the mark scheme, that's exactly what we have. And notice how they'll take both of these conformations. They'll take either F2O or OF2, because that is the formula. If you were to give the Lewis structure, if you were to give this as your answer, you would get that question wrong, because this is not a formula. This is the Lewis structure of this compound, not its formula. So do be very careful with what they're wanting and what they're asking here. And just as as a bit of a review, remember here the command word for this is going to be predict, meaning, were you taught specifically what the formula between oxygen and fluorine compounds are? No. But predict means that you have enough knowledge to use reasoning to figure this out, right? and then make sure that you look at the specific thing that's being asked for, which in this case is the formula, not the Lewis structure. So be very careful with the wording of the question. All right, moving on. Now, nomenclature. Nomenclature is a very varied topic. It's a large topic that we spend a fair bit of time reviewing in honors chemistry, but we're just going to look at a very short overview here. The point of this is not to review all of nomenclature. The point of this is just to give you a refresher. So remember, the nomenclature is going to be based on what type of compound it is. So whenever you're thinking about the name of a compound, the very first question you want to ask yourself is, what type of compound am I looking at? And remember, there's a very easy way of figuring this out, right? Because if we look at these, if it's ionic, if it's an ionic compound, it's going to start with a metal or NH4. So if it starts with a metal or NH4, you know it's ionic. Doesn't matter what the metal is, doesn't matter how many NH4s there are. If it starts with a metal or NH4, it's ionic. Covalent compounds are going to start with a nonmetal or a metalloid, or sometimes called semi-metals, but I prefer the term metalloid. So covalent compounds, if it starts with a non-metal or a metalloid, then we know it's a covalent compound. And finally, acids are going to start with hydrogen, except for the very famous one, which is water. So if it starts with H, other than water, of course, if it starts with H, then, actually, let me just put up here. If it starts with H, then it's going to be an acid. So it should be very easy for you to distinguish whether you're looking at metal, a non-metal, or a metalloid, because all you have to do is look at what it starts with. It starts with Fe, which is a metal, ionic. It starts with N, which is a non-metal, covalent. It starts with H, like H2SO4. Again, doesn't matter how many H's, an acid. Unless, of course, it's H2O. Water is a bit of an exception to this rule. So how do we name the different types of compounds? If it's ionic, all we're going to do is name the ions, right? Whether they're anions or cations, we simply use the name of the cation followed by the name of the anion. Now, for example, here we have FeCl3. One thing you need to remember is that if the cation, if the metal has multiple ions, we are going to use a Roman numeral to give which specific charge or oxidation number, but we'll go for a charge for right now, of that element it is. So FeCl3, for example, we know FeCl3 is made out of iron 3+. How do we know that? Again, if we have one Fe and we have 3 Cls, there is only one ion of Cl. Cl is a group 17 element, so its ions are -1 charge. So if this is -3 in total, then the iron has to be +3 to cancel them out. So this iron 3+, meaning we're going to put iron 3. Why? Because there is a difference between FeCl3 and FeCl2, which is iron 2 chloride. Remember, the Roman numeral here is telling us the charge of that cation, but it is only used if that cation has multiple charges like iron does. If we have something, and I'm going to go up here because I'm running out of space, if we have something like MgSO4, magnesium only has one ion. Magnesium only has a +1 ion. So MgSO4 would be magnesium, no Roman numeral, because magnesium only has a 2+ ion. There's no second ion of magnesium. And then the name of the anion, which in this case, SO4, is the sulfate ion. So this would just be magnesium sulfate. You do need to remember your polyatomic ions in order to do this, though. So make sure that you're going over the list of common polyatomic ions and transition metals that we went over last year. For covalent compounds, it's a bit easier because we don't need to remember all these ions. Covalent compounds are just named using prefixes. We're going to use a prefix to show how many of the element there are. So 1 prefix being mono, for 2 is di, 3 tri, tetra for 4, penta for 5, hexa 6, septa 7, octa 8, nona 9, deca 10. So we're going to use these prefixes to say how many of that element we have, and then the element's name. For the second element on the compound, we are going to change it ending to "-ide". So for example, N2O4, the prefix for 2 is di, so di-nitrogen, meaning 2 nitrogens. And then the prefix for 4 for the oxygen is tetra, so tetra oxide, because we're going to change that ending to IDE. So if it's a covalent compound, all we need to do is remember these 10 prefixes and then remember to change the ending of the second element to IDE. So for example, if we have something like PCl5, which is a thing, and we'll go over why this is a thing in chapter 4. But we have P is phosphorus, and now we only have one phosphorus. Remember, if we have one of the first element, we're not going to use the mono prefix. Mono is only for second element. All the other prefixes we use for everything, but the mono prefix is only used for the second element. So here we're not going to say monophosphorus because it's the first element. We're just going to say phosphorus. And then we have 5 chlorines. The prefix for 5 is penta. So this is going to be penta. Oops. Chlorine is going to have its ending changed to IDE because it's the second element, so it's going to be pentachloride. And that's how we get the name for PCl5. Finally, for acids, the names of acids are going to require you to know the anion names, because the names for the acids are going to depend on the ending of the anion. And there are 3 rules that you learned last year. We're essentially going to name acids after the anion. Why? Because they all start with the same cation, hydrogen, right? Well, they're all going to start with hydrogen, so we need to name them based on the second one, the anion. Now, if the anion ends in IDE, like the sulfide ion here, then we're going to grab the root of the ion's name and then change that IDE ending to "-ic" with a hydro prefix. So H2S, this sulfide ion, we have that root. We're going to change the ending to "-ic" acid, so sulfuric acid, and then we're going to add the hydro prefix, so hydrosulfuric acid, because the ion was sulfide. On the other hand, if the ending of the ion is "-ite", then we're just going to change the ending of the element, or the root of the element, to "-ose". So here we have the SO3 ion, which is sulfite. We're going to change that ITE ending to OUS. So now this becomes sulfurous acid, H2SO3. Why? Because the ion SO3 is sulfite, so we have that ITE ending. And then finally, if the ending for the ion is, and I'm going to change my color here, is 8, like SO4 is the sulfate ion, then if the ending is 8, what we're going to do is we're going to change that ending to "-ic" acid. So H2SO4 becomes just sulfuric acid. And again, we have to be careful because the "-ite" and the 8 are similar. What is the difference? 8 has no hydro in front of it. So the difference between hydrosulfuric acid and sulfuric acid is that the one with hydro has an "-ide" ending. So hydrosulfuric acid is a sulfide ion, so H2S. Sulfuric acid, without the hydro, is originally the sulfate ion, so H2SO4. And then how do we know how many hydrogens we have? Remember, hydrogen is always H+, so +1. So whatever the charge on the anion is, that's how many hydrogens we put. So here we have 2 hydrogens in all of these because all of these anions have a -2 charge. If we have something like NO3, for example, this is only 1 H because NO3 is -1. This is a nitrate ion. And so if we want to name HNO3, because we have that 8 ending, we just change the root we change the ending to ic. So the root here is nit. So nitric, we change that ending, acid. I also adding the word acid to the end of the acid name. All right. So that's just a brief throwback, brief overview of the nomenclature rules. Remember, first question you should ask yourself, is it ionic, is it covalent, or is it an acid? If it starts with a metal or with an H4, it's ionic. If it starts with a non-metal or a metalloid, it's covalent. And if it starts with hydrogen and it's not water, it's an acid. Water, by the way, is covalent. And then we use these different naming rules depending on which one it is. So I'm going to keep going here. So we have here an example of how would we go about using this. Because again, it's not going to be as simple as what is the name of H2O, right? They're not going to ask you the question that's that direct. But they will ask you for things like constructing an equation where they give you all the information. The information is in name format. So let's look at this. I'm going to bring this over here. So here we have solid ethane dioic acid reacts with aqueous calcium ions to make a precipitate of calcium ethane dioate, CaC2O4. Now this alone, because we haven't even covered organic yet, can seem very challenging and it can seem very scary because you have all these big words, ethane dioic acid, right? And it's reacting with calcium ions to make a precipitate of calcium ethane dioate. Like, these are really complicated sounding compounds. But if you keep reading, you'll figure out that that's not the point here. We have calcium CaC2O4, which is that calcium ethane dioate, breaks down when heated to form calcium oxide, carbon dioxide, and carbon monoxide. Construct an equation to represent the reaction of CaC2O4 when heated. Include state symbols. So right away, here we are being asked. First of all, let's look for that command word. The command word here is construct. Again, construct does not mean that you know this already. Construct means that you're using knowledge from before to build an equation, to build something up, right? You have the knowledge, you have to put it into practice. Now, when we read this, we'll realize that it says, let me switch over to this. So you'll realize that here it says an equation to represent the reaction of CaC2O4 when heated, meaning we're talking about here, this right here. CaC2O4 breaks down when heated to form calcium oxide, carbon dioxide, and carbon monoxide. Meaning all of this information up here, we can ignore this right now. We don't need to know any of this. We might need to know it for like BII or BIII, but we don't need to know for this particular question. And that's very important. Focus on the things that you actually need. And then we can read what it actually says. CaC2O4 breaks down when heated, meaning this is a decomposition reaction. And if you learned anything of decomposition reactions last year, is that they have only one reactant. So we know CaC2O4 is the only reactant. CaC2O4. And that's going to break down when heated. And because it's heated, we'll put a little delta or that little triangle on top of the arrow. And they actually tell you what the reaction is. You don't have to predict products here. They tell you, breaks down when heated to form calcium oxide, carbon dioxide, and carbon monoxide. Meaning we don't need to actually know how this reaction works. All we need to know is nomenclature. We need to know how to name compounds. Because they're telling us what the products are. They're telling us there are 3 products and this is what they are. So all we need to say is, okay, what is calcium oxide? Well, I'm starting with metal, so it has to be ionic. So I'm going to look at the ions. So calcium being in, and I'm going to bring over my periodic table. Calcium being in group 2 is going to have a 2+ charge. Calcium is right here. And that's not have a 2+ charge because it's in group 2. So we have the ion of calcium, which is a Ca2+, And then we have oxide, which is the ion again, because remember, monoatomic ions, that ending is going to be changed to IDE if there are anions. So the oxide means the oxygen ion, which is, oops, we have all these things over here. So the oxygen ion is O. Let me erase all of these. So we have calcium over there in group 2 reacting with oxygen over here in group 16. So we're going to have here calcium, which is a 2+ ion. Oops, let me make that smaller. So a 2+ ion because in group 2 with oxygen, which is going to be -2 because in group 16. This is when it becomes important knowing what charges the representative elements make. So we're going to have, we're going to have these calcium 2+ that we wrote here reacting with the oxide, which is O2-. When we cross them, we end up with Ca2O2. But remember, we need to simplify these ratios when we can. So Ca2O2 becomes just simply CaO, a 1-to-1 ratio instead of a 2-to-2 ratio. So here our first product, without us having to think of how the reaction works, is CaO plus carbon dioxide. Now we should all know what this is, but just for the sake of practice, because we're starting with a nonmetal carbon, this is going to be covalent, meaning the prefixes tell us how many of the element we have. So carbon, not having a prefix for the first element means that we just have one carbon. Di means 2. Oxide being oxygen, because remember the ending is changed for the second element. So it's just going to be CO2. So that's our second product. Plus carbon, again, one carbon because there's no prefix. And again, it's carbon, so it's covalent. Monoxide, mono meaning one, oxide again meaning oxygen, so carbon monoxide meaning just CO. So just from that, we can get the reactant, because we know it's a breakdown, meaning it's a decomposition reaction is one reactant, and then all of our products. All we need to do now is balance it, which we'll go over in the next section, but we should all remember how to balance from last year. And we can look here, we have one calcium, one calcium. 2 carbons, 1, 2 carbons. 4 oxygens, 1, 2, 3, 4 oxygens. So this is already balanced. I don't even need to balance. Now I do need to include one more thing. This has to include state symbols. Remember, state symbols means state of matter symbols. So we need to figure out what these things are, what the state of matter there. Now, for some of these, it's going to take some thinking. For others, it should just be something that you know in the back of your head. Mainly, carbon dioxide, which you have talked about in biology, in chemistry, in middle school. You should know carbon dioxide is a gas because you exhale it, it's in the air, blah, 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 etc., etc. Carbon monoxide might be a little more unfamiliar to you, but carbon monoxide is also going to be a gas. On the other hand, the two ionic compounds, let me bring this back up, the calcium oxide and the calcium CaC2O4, because they're ionic compounds, we need to remember ionic compounds are always solid. So these are always going to be solid states of matter when you have an ionic compound. And you need to keep that in mind. All right? Ionic compounds are always solid. Carbon monoxide, carbon dioxide, you should know just from experience, are gases. And so here our formula is simply CaC2O4 yields CaO plus CO2 plus CO. Now you get 1 point for having the correct formulas, again nomenclature, and a second point for the balancing, which is all ones, and the state symbols. So these should be 2 very easy points for you to get on the AS exam. All right. All right, so let's look at the next topic. So speaking of balancing equations, the atoms of each element in the products and reactants side of a chemical equation always have to be equal to each other. That's where balancing equations comes in. Again, a topic from honors chemistry. Remember that when we write these atoms or these molecules and formulas into a chemical equation, we need to use coefficients in order to balance them out. We use coefficients with our whole number ratios between the elements to make sure that we don't destroy or create any matter, that the same number of atoms of one element are in this other side. Or, remember, we can see these whole numbers, these coefficients, as atoms or molecules, or we can see them as moles. So how many moles of one compound react with moles of another to create how many moles. When possible, we should always try to use states of matter in questions as well. We call these state symbols. So apart from the coefficients, we're going to have those state symbols or the states of matter of the elements and compounds to indicate the state of matter of each chemical. Because there are going to be two situations you're going to encounter. There are going to be a lot of questions on the AICE exam which ask you for a chemical formula or a chemical equation, such as this one. And when you look at the mark schemes, they're not going to have the states of matter. And in that type of question, which usually they wouldn't tell you to put the states of matter, they'll just tell you to give the equation. In that type of question, then the points are for the actual chemicals and the balancing. And then there's going to be questions where they tell you to put the states of matter. And they will be a point. The states of matter, like the question we saw earlier, will be a point on the AICE exam question. Now, there are going to be some tricky questions where they don't ask you for the states of matter, but it's kind of implied that you should include them, and they are a point in the answer. So, in all three of those scenarios, if you put the state of matter, you will either get points for them, or they won't be scored, meaning that if they're wrong, they'll just ignore them anyway, and you won't get the points for them. Or, in one of those scenarios, if you don't put the states of matter, you won't get points. So whether they ask you for the states of matter or not, it's a good idea to put them, because either you get points for them if they're right, or if they're right and you don't need them, you just won't get points for them. Or if they're wrong and you don't need them, you won't get points for them. But it's always a good idea to add them just in case, because it shouldn't take you too long to do so. Now, in certain situations, a few rules of thumb that we can have with this is that anything that's ionic, unless they tell you it's a solution or that it's aqueous, anything that's ionic is going to be solid. And that there are common gases that you should remember. Carbon dioxide, carbon monoxide, methane, are some of ammonia and H3 are some of the common gases you should remember. You had a list of common gases last year that you can keep referencing. They're in the classroom, they're in your notes from last year in honors chemistry that you can reference that are common gases. But you should commit some of these to memory. Liquids, we don't have to worry about too much. The things that are liquids, they'll either tell you they're a liquid, which we'll go more over when we go into organic chemistry, or they're either mercury, bromine, or water. Those are the only other three common liquids that we work with. Water being obvious, mercury and bromine being the only two elements in the periodic table that are liquid in their natural state. But let's go back and look at the balancing of this equation. So this equation can look tricky to balance because there's a lot of elements here. But one of the things that you got to remember that's going to help you with the balancing is that if you see a polyatomic ion like nitrate, NO3, that is still present in its full state, meaning it didn't get broken down, on the opposite side, you can treat that nitrate as just one thing. So instead of balancing the nitrate and the oxygen separately, we can balance the nitrate as a whole. So we have the nitrate, we have the lead that we need to balance, and we can follow that by looking at the color coding. We have our iodine, which is here and here. And we have, a different color, the sodium. So again, the goal of balancing is making sure that there's the same number of elements on both sides. So here we have 4 nitrates, and we only have 1 nitrate, NaNO3. So we can go ahead and put a 4 coefficient in front of NaNO3, because that's gonna, again, make sure that we remember this correctly, that 4 coefficient is going to affect everything, meaning we're going to have 4 nitrates, which is what we want because we have 4 nitrates on this side, but we're also going to have 4 sodiums. That means that on this side, we need to put a 4 in front of the NaI because the 4 sodiums here need to be balanced out on this side. So the 4 sodiums are going to balance out, but then that 4 also goes to the iodine, which gives us 4 iodines, which we have on this side. That gives us 4 iodines, 4 iodines, 4 sodiums, 4 sodiums, 4 nitrates, 4 nitrates, and then 1 lead here, 1 lead here. So with those two 4s, this equation is balanced. And ionic compounds, or ionic equations with ionic compounds, are very easily balanced for the most part. The ones that are harder to balance are going to be these combustion reactions that we dealt with last year. Remember that with combustion reactions, you might get into a weird point where you might have to use a decimal and then get rid of it by multiplying. So here we have C4H10 reacts with O2, and again, oxygen is a gas normally, to create carbon dioxide, naturally gas, and water. Now this water is a gas. Why? Because it's a combustion reaction. It gives off a lot of heat and it evaporates the water. So things like that, those kind of logic, you should also be able to follow. So here we are going to put a 4 in front of CO2. Why? We have 4 carbons here, so we need 4 carbons here in the CO2. So that's 4 carbons, 8 oxygens in total. 4 times 2 is 8. Well, that's balanced out the carbons. Always start by balancing out with combustion reactions the hydrocarbon, this thing that we're burning in oxygen. So we have 4 carbons here. We're now going to balance out the hydrogens. We have 10 hydrogens here. We have H2, so we're multiplying our coefficient times 2 for hydrogen, meaning we're going to put a 5 in front of the water, because 5 times 2 gives us 10 hydrogens. Now, this is where things get weird when we start looking at the oxygen, because here we have, let me grab my pencil here, we have 4 times 2 is 8 oxygens. Now, let me use a different color. 4 times 2 is 8 oxygens. 5 times 1 is 5 oxygens here. Let me put a little loopy so we don't confuse this for zeros. So we have 8 plus 5, that's 13 oxygens in total on the product side. The problem here is that the oxygen on the reactant side is at O2. We can multiply anything times 2 to get 13. That's a whole number. So what are we going to do? Instead of starting all over again, we're going to put here a 6.5. Why? 6.5 times 2 is 13. Right? And that gives us the 13 oxygens. Now, the only issue with this is that we can't use a decimal as our coefficient. So what do? We just get rid of the decimal. How do we do that? We multiply every coefficient that we have here times 2. So 6.5 times 2 is 13. 4 times 2 is 8. 5 times 2 is 10. And then we can't forget about this here, that C4H10 also had a 1 in front of it. So we need to multiply this times 2 to make it a 2. Let me move it in red. So we can have a 2 here. And then you'll see that by doing this, these coefficients actually fix themselves. Why? We have 2 times 4 is 8 carbons. 8 times 1 is 8 carbons. 2 times 10 is 20 hydrogens. 10 times 2 is 20 hydrogens. And then we have 13 times 2 is 26 oxygens. Here we have 8 times 2 is 16, plus 10 times 1, which is 10. 16 plus 10 is 16 oxygens. And this is all now balanced. So do try to practice balancing if you did not master it last year, because it is a skill that will essentially be second nature in this whole year. You will be expected to be able to balance an equation. And you'll find that there are going to be questions in this year that if you can do that, it will ruin your chances to even answer that question. Now, the last topic we're going to go over again is ionic equations. Now, in AS chemistry, or sorry, in honors chemistry, we call these net ionic equations. But Cambridge does not use the net, it just uses ionic equations. Do realize they mean the exact same thing. Net ionic equations, it's the same thing in Cambridge. Remember, ionic equations are those which only show the ions in ionic reactions where the ions are actually reacting. All other particles or ions that are not reacting are not shown. We call these spectator ions. Spectator ions are ions present in a reaction mixture which do not take part in the reaction itself, meaning they're simply there to bring in the ions of that compound. So we can follow the steps here outlined on the right side, which you learned last year again, so I'm not going to go over it too in depth, but to give a basic overview, in order to create an ionic equation. For example, step one, or actually not for example, so the steps we follow are: step one, we write down the full balanced equation, right? So here we have the reaction between magnesium and hydrochloric acid. Magnesium, which is a solid, and again, why is it a solid? Use your logic. Magnesium's a metal. The only metal that's not a solid is mercury, so this is a solid. Plus 2HCl aqueous. Why is this aqueous? It's an acid. Acids are always aqueous. Yields MgCl2 aqueous. Why is this aqueous? It's an ionic compound, but we have water because we already said this was aqueous. So magnesium chloride being soluble is going to be aqueous. Plus H2 gas. Why gas? Because hydrogen is one of those common gases we need to remember. So this is the full balanced equation. Now here, one of these ions is actually not going to be reacting here. It's just simply there to carry in whatever partner ion it is paired up with in the ionic formula, or in the acid in this case. So the step two is going to be to go and look at your full valence equation and separate anything that is either ionic or an acid and that is aqueous. So separate all ions present. Magnesium solid stays magnesium solid because that's not an ionic compound, it's not an acid, it's just going to stay exactly how it is. HCl is an acid and it's aqueous. So we're going to separate the HCl into the two ions that make up HCl. Hydrogen ions, which are H+, and again, that coefficient, that 2, is going to be applied to everything. So when we separate this, that 2 is going to count both for the hydrogen, so we put 2H+ aqueous, and for the chloride, Cl-, so we put 2Cl- aqueous. On this side, we have MgCl2, which is ionic, so I'm going to mark this because it's an acid and aqueous, and it's ionic and aqueous, so we separate MgCl2. MgCl2 is made out of 2 plus magnesium, Mg2 plus aqueous. And then that 2 only applies to this chlorine because there is no Cl2 ion. So that 2 is just telling us we have 2 chlorines here. So we have 2 actually chlorides because it's the ion. So 2Cl- aqueous, right? Because that 2 came from this 2 right here. And then the hydrogen gas is not ionic compound, it's not aqueous, it's not an acid, so we just leave it exactly how it is. So step number 3 here is going to be to realize that out of this whole thing, when we separate all the ions, the chloride ion is actually exactly identical on both sides. We have 2Cl- aqueous in the reactants, 2Cl- aqueous in the products. Because the chloride ion does not change, it makes it a spectator ion. It's an ion that does not actually participate in the reaction, but instead it's just there to bring in the hydrogen from the hydrochloric acid. So how do we write the ionic equation, or the net ionic equation is what we called it last year? How do we write this ionic equation? All we have to do is get rid of that spectator ion, which is chloride, and rewrite the equation like we had it. The magnesium stays because magnesium goes from a magnesium solid to magnesium 2 plus aqueous, so it does change. The hydrogen changes from 2H plus aqueous to H2 gas. It does change. The only thing that does not change is the chloride, so we remove it for the net ionic equation, or again what Cambridge just calls the ionic equation. Now, a lot of the time you won't have to come up with ionic equations. That is a fair misunderstanding. There are going to be some questions once in a while that ask you for that. But for the most part, what you need to be able to do is look at the equation and understand the context. For example, the reaction between permanganate and iron is as follows. MnO4 minus reacts with 5Fe2 plus and 8 hydrogen ions to create Mn2 plus plus Fe3 plus plus water. And this will be 5 Fe2 plus, and this is going to be 4 waters. So this is a reaction between permanganate and iron. Now the problem here is that they're not going to tell you in the S exam, in the wording, in the question, they're not going to say the reaction between permanganate ions and iron 2 plus ions. They're going to speak of this as the reaction between potassium permanganate plus iron to, let's say, sulfate. Or actually, that's better yet, chloride. So they might speak and they may give you the whole question. The preface asks the reaction between potassium permanganate and iron 2 chloride. And then you're staring at this, you're going, wait, where did the potassium go? Where did the chloride go? They're not in the equation. And that's going to confuse you. You have to realize that what this is the ionic equation for this reaction. The potassium is not there because the potassium is a spectator ion. The chloride is not there because the chloride is a spectator ion. This permanganate from the potassium permanganate is what's reacting, not the potassium. This iron 2 from the iron 2 chloride is what's reacting, not the potassium. Not the chloride, sorry. So because the chloride is a spectator ion as well as the potassium. So being able to look at that and say, okay, that's where this is coming from, not being confused, that's the main point where ionic equations are going to come in. Not so much coming up with them, although you could be asked to do that, but more importantly, being able to read them and not get lost into the where the potassium go, where did the chloride go. Because understanding that these are spectator ions allows you to ignore them when you're doing the chemistry and the mathematics for this. All right. Well, that's it for section 3.6. We'll see you in the next video when we do 3.7. But that is everything for this video. I will see you all next time.